Welcome to the Introduction to Networking course. In this course, we'll cover the basics of networking. We'll start with what is a network and why it's needed. Next, we'll describe the network components and provide the requirements for a networking solution, especially in highly demanding environments. Lastly, we'll introduce the OSI model and the TCP/IP protocol suite and their role in networking. We have a lot to cover, so let's start. A network is a collection of nodes connected together so that they can exchange data such as voice, video, storage, or management. Applications running in modern data centers have unique performance requirements. The network must be able to provide the performance expected by the running applications, such as high bandwidth and low latency. In addition, the network must be highly available and scalable to support future growth. This is not an easy task. So, how do we create a network? Network components include the end nodes and intermediate nodes. The end nodes include compute, storage, and management nodes. These are the source or destination of the traffic carried in the network. The intermediate nodes, such as switches and routers, receive the traffic generated by the end nodes and make decisions as to where the traffic should be forwarded. Let's see how a simple network is formed. Every end node has a network interface card, or NIC. The NIC is a hardware component that resides in a slot and has one or more network ports. The next step would be plugging a cable into the NIC port on one end and into a switch port on the other end. Great! Now we have the end nodes physically connected. But how do they communicate? For the end nodes to be able to communicate with each other, an example sending and receiving traffic, they must implement the same communication protocols, where each protocol is responsible for a specific set of activities. Each protocol defines a set of communication rules, such as how the communication session is set up and terminated, what is the message format, and how errors are handled. There are many protocols for different purposes, and we are not going to cover them all. A group of protocols that run concurrently to implement network communication is called a protocol suite. Different protocol suites are different combinations of protocols that are used for different communication types. Later, we'll introduce the main protocol suites used in today's networking deployments. Considering all the hard work that a network is expected to do, it is easier to break down the different functionalities of network communication into layers, in order to make communication easier. The Open Systems Interconnection, OSI, is an ISO standard model that describes 7 layers that computer systems use to communicate over a network. It is a generic, protocol-independent standard that was the first standard model for network communications adopted by all major computer and telecommunication companies in the early 1980s. If you've heard already about a Layer 2 device such as a switch or a Layer 3 protocol such as IP, they all refer to the respective OSI layer. We'll cover some of those later. There are many advantages to a layered model. Some are listed here. Another networking-related model is TCP/IP. The TCP/IP model is, in a way, an implementation of the OSI model, since it's provided with a suite of protocols that enable end-to-end data communication services. When comparing the two models, we see that TCP/IP, the physical and data link, are both combined as a network access layer. Also, there is no session or presentation layer in the TCP/IP model, so the 3 upper OSI layers are combined into a single application layer. In the 1970s, the US Department of Defense developed a network called ARPANET that enables data transport between computers at different locations by creating alternate routes. TCP/IP was used as the system protocol for that network. ARPANET ceased to exist in 1990, but since then, TCP/IP has evolved to meet the changing requirements of the Internet. TCP/IP specifically defines how computers should be connected to the Internet and how data can be transmitted between them. TCP/IP protocol suite is named after 2 of the main protocols: TCP, Transmission Controlled Protocol, and IP, Internet Protocol. The TCP/IP suite is a set of communications protocols used on the Internet. It includes protocols that specify how data is packetized, addressed, transmitted, routed, and received, thus providing end-to-end data communication. Shown here are some of the protocols in the suite, where each protocol is listed at their respective layer. Please note that TCP/IP model has 4 layers as opposed to the 7-layer OSI model. Layers of the different protocols should always be referenced to the OSI model. For example, the Internet Layer protocols, IP version 4 and IP version 6, are considered Layer 3. Similarly, the Transport Layer protocols, TCP and UDP, are considered Layer 4 protocols, and application layer protocols such as HTTP and FTP are referred to as Layer 7 protocols. We'll cover some of these protocols in more details in the following units. In order to understand how data is transmitted between applications, it's important to understand what encapsulation is. Sending application creates messages that are passed to a production line of the lower layers, where each layer adds its relevant information in a process known as encapsulating the data with a layer header. Header is the supplemental data placed at the beginning of a block of data when it is transmitted. The supplemental data is used at the receiving side to extract the data from the encapsulated data packet. This packing of data at each layer is known as data encapsulation. By the end of the encapsulation process, the encapsulated data is transmitted on the wire. Each layer is associated with different protocols: PDUs, protocol data units, addresses, and devices. Let's see these for each of the layers. The data generated at the application layer for network transmission is referred to as a message. A message is then encapsulated at its lower layer, the transport layer. The transport layer adds a layer 4 header that includes fields such as port numbers that are relevant for transport layer processing at the receiving nodes. A message encapsulated with a layer 4 header is called a TCP segment or a UDP datagram. These are the layer 4 PDUs. A TCP segment or a UPD datagram is handed over to the internet layer and is further encapsulated with the layer 3 header, containing, for example, source and destination IP addresses. The layer 3 PDUs are called packets. Packets are routed in the network by layer 3 devices called routers. Packets are then passed down to the data link layer that adds a layer 2 header. Layer 2 PDUs are called frames. The most important values in the data link layer header are source and destination MAC addresses. Frames are forwarded in the local network by layer 2 devices called switches. The frame is then transferred to the physical layer, layer 1, and is converted into a stream of bits. The stream of bits is then placed on the network medium for transmission. We've used many technical terms to describe the flow of data transmission. No worries if you're not familiar with some. We'll cover them in more details later. At this point, it's only important that you understand the general flow. Throughout the course, we'll use standard icons to represent typical network components. Please take the time to review them and make sure you are familiar with them. Welcome to TCP IP Protocol Suite course. In this course, we will introduce top-down some of the most used TCP IP protocols. We will start with application layer protocols, such as HTTP and FTP. Then we will move on to TCP and UDP, the transport layer protocols. Lastly, we will present IP, the Internet Layer Protocol, and some supplemental IP services that are crucial to IP-based networks. Let's start with application layer protocols first. We need to keep in mind that the main goal of having a network is data transfer. Let's see how it works. We have two remote applications that generate messages, and those messages are exchanged between the two applications. For the applications to be able to understand each other, they must implement the same protocol. One example of this concept would be using a web browser to view web pages. On one end, the application is the web browser, and on the other end, the application is the web server. When the user inserts the web page address in the browser's address bar, in the background, it is converted to a request in a format that the web server can understand. Once the request is received by the server, it will respond with the page details in a format that the browser could present in text or links. There are many different applications with different purposes and requirements. For each application, there is an application layer protocol that provides the interface to the networking services. Whenever an application layer protocol wishes to communicate with a remote application, it hands over the data to the transport layer. Some application layer protocols use TCP as the transport layer, while others prefer UDP. More information on TCP and UDP will be provided in the next section. We have previously used the example of a web browser asking for a web page from a web server. We already know that for the communication between the two to happen, both the web browser and server must implement the same application layer protocol. This protocol is called HTTP, Hypertext Transfer Protocol. HTTP allows exchanging text and hyperlinks. It also has a secure variant called HTTPS. HTTP functions as a request-response protocol in the client-server computing model. The client submits an HTTP request message to the server. The server, which provides resources such as HTML files and other content types, returns a responding message to the client. The response contains the request completion status information and may also contain requested content in its message body. FTP is an application layer protocol used to transfer files between hosts. FTP users may connect anonymously if the server is configured to allow it, or may authenticate themselves with a clear text sign-in protocol, normally in the form of a username or a password. FTPs can be used for secure transmission that protects the username and password and also encrypts the content. We've seen that for communication between two applications to happen, the messages are formatted into an application layer protocol. The next step is for the application layer protocol to ask transport layer services. Let's see how it works. Transport layer protocols are responsible for establishing end-to-end logical communication channels between the source application and the destination application. The functions of the transport layer are facilitating the communicating hosts to carry on a conversation, providing an interface for the users to the underlying network. If needed, it can provide a reliable connection. It can also carry out error checking, flow control, and verification. The two most commonly used protocols are TCP and UDP. We will see further details, including the differences between the two, in the following slides. TCP is a reliable connection-oriented transport protocol. Connection-oriented means that a connection is established between the peer entities prior to transmission. To assure data transfer reliability, TCP uses sequence numbers and acknowledgements to recover from damaged or lost data. Another important mechanism provided by the TCP is flow control. The flow control allows a busy receiver to govern the amount of data sent by the sender. TCP uses a window size to indicate the allowed number of bytes the sender may transit before receiving further permission. Lastly, TCP sequence numbers are used to order segments, hence providing ordered delivery. All those mechanisms have multiple advantages, and indeed, many applications that require reliability use TCP as their transport layer protocol. However, there is a trade-off, as it is associated with overhead and therefore data transfer slows down. For applications that require fast, lightweight transport service, TCP may not be the best choice. When a client needs to connect to a remote server using TCP, first, a connection must be established. Once a connection is established, data can be transferred. TCP uses a keep alive feature to keep connections open and manage them. The keep alive feature verifies that the peer at the other end of a connection is still available. After the data is transmitted, the session is terminated and the allocated resources are released. A three-way handshake is a method used in TCP IP network to create a connection between peers. It is a three-step method designed to allow both communicating ends to initiate and negotiate the parameters of their connection before data such as HTTP and SSH is transmitted. It requires both peers to exchange 3 synchronization and acknowledgement messages before actual data communication begins. Step 1. The client sends a synchronization message to the server. The objective of this message is to ask or infer if the server is open for new connections. Step 2. When the server receives the synchronization message from the client, it responds and returns a confirmation receipt, the acknowledgement message or SYN-ACK message. This acknowledgement indicates that the server correctly acknowledged the client's message and that it is sending its own synchronization to be acknowledged as well. Step 3. The client receives the SYN-ACK from the server and responds with its own acknowledgement message. Once again, each side must acknowledge the synchronization message of the other side. Upon completion of this process, the connection is created, and the client and server can communicate. TCP is reliable since the protocol ensures that data is not damaged, lost, duplicated, or delivered out of order. Otherwise, it must recover it. TCP ensures that all data is fully transmitted and can be assembled by the receiver in the correct order. TCP achieves this reliability by assigning a sequence number to each byte it transmits and requiring a positive acknowledgement from the receiving peer. If the acknowledgement is not received within the timeout interval, the data is retransmitted. At the receiver, The sequence numbers are used to correctly order segments that may be received out of order and to eliminate duplicates. Let's see a small example of how sequence and acknowledgement numbers are used. For this specific example, we will assume that when the session was established, it was agreed that the segment size is 10 bytes, and that the sender can send 30 bytes before expecting to receive an acknowledgement from the receiver. In our example, the sender sends 3 segments of 10 bytes each. The sequence for the first segment is 0, representing the first 10 bytes numbered 0 to 9. The sequence number for the second segment is 10, representing bytes 10 through 19. And the sequence number for the third segment is 20, representing bytes 20 through 29. If the first 3 segments, or 30 bytes, numbered 0 to 29, were correctly received in a defined interval, the receiver will send acknowledgement number 30, indicating it is expecting byte number 30 to be received. Now, let's assume that the second segment arrived damaged or got lost. In that case, the receiver would ask for its retransmission by sending back ACK number 10, telling the sender it is expecting byte number 10. This is a very simplified example just conveying the idea of how TCP uses sequence and acknowledgement number to provide reliability. Also, we've shown only one side of the communication, but since TCP sessions are bidirectional, data is sent in both directions. Now let's assume that the second segment arrived damaged or got lost. In that case, the receiver would ask for its retransmission by sending back acknowledgement number 10, telling the sender it is expecting byte number 10. Another mechanism provided by TCP is flow control. First, let's understand what is the meaning of flow control and why do we need it. Let's assume a scenario where the sender sends data in a faster rate than the receiver is capable to process. In this case, the excess data is dropped and TCP will require retransmits. To avoid such a scenario, a flow control mechanism can be implemented. Flow control is a process of managing the rate of data transmission between 2 nodes to prevent a fast sender from overwhelming a slow receiver. The idea is that the receiver will send feedback to the sender to let it know about its current condition. Let's see how TCP flow control works. To control the amount of data that the sender sends, the receiver will advertise its receive window size, that is, the spare room in the receive buffer, or the number of bytes it is prepared to receive before an acknowledgement is sent. In this example, the receiver acknowledges the first 30 bytes with acknowledgement number 30, and reports to the sender that it can receive an additional 30 bytes with window size 30. The sender sends the next 30 bytes in 3 segments of 10 bytes each. Now the receiver acknowledges the next 30 bytes with acknowledgement number 60, and reports to the sender that it can receive an additional 20 bytes with window size 20. As a response, the sender will now send 20 bytes or 2 segments of 10 bytes each. It is important to notice that the window size is dynamically adjusted, increased or decreased as needed. Once again, we have seen only one side of the communication, but since TCP sessions are bidirectional, data is sent and received in both directions. This means that each side controls its receive window size independently. We have covered many mechanisms supported by TCP to provide reliability, but it all comes with a price, as TCP consumes more resources, uses more network bandwidth, and results in a slower transfer. User Data Protocol, or UDP, on the other hand, allows applications to transfer data with minimum protocol overhead. With UDP, data is continuously sent to the recipient, whether it is ready to receive it or not. Retransmission of lost data is not supported, and packets arrive out of order. UDP avoids the unnecessary overheads of TCP transport. It is incredibly efficient in terms of bandwidth and much less demanding of poor-performing networks as well. Although UDP is not ideal for sending an email, viewing a web page, or downloading a file, it is largely preferred for real-time applications like voice or video. One thing that TCP and UDP have in common is that they both use source and destination port numbers to identify the specific process within the local and remote nodes. The destination port is a well-known number, identifying the service requested on the remote server. The source port is a dynamically allocated number identifying the process that sends the data. Let's see how port numbers are used. We have a single server that runs 2 services, HTTP and FTP. When a client generates a request targeted at that server, The client must specify which service is requested, either HTTP or FTP. In this example, the client generates an HTTP request for a web page. When this request arrives to the server, it must be able to identify that it is an HTTP request and forward it to the HTTP service. Only the HTTP service can respond to the HTTP request. In the request generated by the client, the destination port number is the field that identifies the service requested at the destination node. For HTTP, the well-known port number is 80. It is customary to say that HTTP servers listen to port 80. As you can see in the request generated by the client, a source port is also present. The source port is a dynamically allocated number identifying the process that sends the data, since many active concurrent processes are supported. Please note that when the server responds, the destination and source port change places, so the HTTP server responds with source port 80 in the destination port of the sending process. Port numbers are 16-bit in size, hence ranging from 1 to 65,535. 0 is reserved. Port numbers in the range of 0 to 1023 are the well-known ports that are used by common TCP IP applications. Some examples of well-known port numbers are listed here. We are done with the transport layer protocols. TCP and UDP are now ready to move onto the internet layer. IP version 4 is a network layer protocol. There is another version of IP known as IP version 6, but it is outside the scope of this course. So IP provides network services to layer 4 protocols, such as TCP and UDP, and in return asks layer 2 protocols to carry the packets over the physical medium. IP is a best effort protocol, and hence relies on upper layer protocol mechanisms. As such, it does not include mechanisms for reliability, flow control, and sequencing. Just a reminder, the internet layer provides the functions necessary to deliver a packet from a source to a destination over an interconnected system of networks. While transport layer protocols operate end-to-end, internet layer protocols operate between any two directly connected layer 3 nodes. An example, an end node and its directly connected router, or a router and its neighboring router. In order to fulfill this function, internet layer protocols should define the following: layer 3 addressing, layer 3 packet format, routing functionalities when routing occurs one router after another, or hop by hop. In an IP network, every network interface of a node is assigned with an IP address. An IP version 4 address is a sequence of 32 bits divided to 4 groups of 8 bits per group, known as octets. For a more readable representation, the 4 octets are separated with dots, and each octet is represented by its decimal equivalent, also known as the dotted decimal notation. IP addresses contain 2 parts. Network address identifies the systems that are located on the same subnet, and host address, which identifies a specific host within the subnet. All hosts in the same subnet share a common subnet address. Every router interface defines an IP subnet. In this example, we have a router with 3 network interfaces, hence 3 subnets are defined. The network address for all hosts in subnet A is 192.168.1.0, where the 4th octet represents the host's unique address within the subnet. Routing is the process of choosing the best path to reach a destination. A router is a computer that has been dedicated to the task of forwarding IP packets between networks. A router makes forwarding decisions based on its forwarding database called a routing table. The routing table includes entries that map remote IP networks to next hop routers that are identified by local interfaces. Routing occurs one router after another, or hop by hop. This concludes the discussion on TCP/IP protocol suite. We've seen how the application layer protocol formats the message that needs to be carried over the network. The application layer protocol then requests transport services from the transport layer. The transport layer adds a layer 4 header and requests network services from the network layer. The network layer, IP, adds a layer 3 header. Now the IP packet is ready to be carried over the physical medium. The specifics of that are defined in the network access layer. Even though IP is a medium-independent protocol, meaning it can be carried over different media types, the most commonly used one is Ethernet. We'll cover the details of Ethernet in the next unit. Welcome to the Ethernet Fundamentals unit. In this unit, we'll cover the basics of Ethernet technology and understand how data is forwarded in an Ethernet network. We'll start with Ethernet technology evolution and standards. Later on, we'll detail some Ethernet specifics, such as how Ethernet nodes are identified using MAC addresses and Ethernet frame structure. Then, we'll describe how Ethernet switches build and maintain their forwarding tables called MAC address tables that are used to forward frames in the network. Ethernet operates in the data link layer and the physical layer of the OSI model. The data link layer provides the functional and procedural means to transfer data between network nodes and the means to detect and possibly correct errors that can occur in the physical layer. The physical layer defines the electrical or optical properties and the transfer speed of the physical connection between network nodes. Ethernet has become the predominant LAN technology thanks to its ability to evolve and deliver higher levels of performance while also maintaining backward compatibility. Ethernet is designed to suit the needs of a broad range of applications, ranging from home networks to corporate LANs to data center interconnects. Naturally, each type of application has unique requirements and protocols that it needs to support. Ethernet was introduced in the 1970s by a team led by Robert Metcalfe at the Xerox Corporation's Palo Alto Research Center in California. In the mid-1980s, the Institute of Electrical and Electronics Engineering, IEEE, published a formal standard for Ethernet defined as the IEEE 802.3 standard. This standard defines rules for configuring an Ethernet network and specifies how the elements in an Ethernet network interact with one another. By adhering to the IEEE standard, network equipment and network protocols from different vendors can communicate efficiently. Ethernet's original 10 megabits per second throughput increased to 100 megabits per second in the mid-1990s, and currently it supports up to 400 gigabits per second. Ethernet allows nodes that are connected to the same LAN to communicate with one another by sending Ethernet frames to each other. In order to achieve this, Ethernet nodes must be identified with a unique address, known as the Media Access Control Address, or MAC. Every Ethernet frame that is generated by the sending node contains a source and destination MAC address in its header. The frame is then forwarded based on where the destination node resides. A network interface card, or NIC, is a hardware component that connects a node to the network. The NIC allows nodes to communicate over the network, either by using cables or wirelessly. The NIC is both a physical layer and data link layer device. At the physical level, it provides access to the physical medium. At the data link level, it provides a low-level addressing system using MAC addresses. A Media Access Control Address is a unique identifier assigned to a network interface for use as a network address in communication within a local network. A MAC address is burnt on the network adapter's hardware by the vendor. The Ethernet standard requires that every Ethernet vendor register with IEEE and to be assigned with an OUI, organizationally unique identifier. MAC addresses are 48 bits long, represented in 12 hexadecimal digits. They have two halves. The left 6 digits form the OUI, and the right 6 digits form a serial number assigned by the vendor. Combining a unique OUI and a unique serial number yields an address that uniquely identifies an Ethernet interface in the network. You can use the following commands in order to identify MAC addresses of network interfaces. On a Linux system, use the ifconfig command. On a Windows system, use the ipconfig command. The MAC address is listed as a series of 12 hexadecimal digits, where each pair is separated by either a dash or a colon. The data link layer is responsible for data transfer over the physical medium, hence an Ethernet frame that can be carried over the Ethernet network created. The Ethernet standard defines the structure of an Ethernet frame as follows. Payload, the protocol data unit received from the upper layer. It's the part that is encapsulated with the layer 2 header to construct a frame. The header includes 3 fields: destination MAC address, which specifies the node for which the frame is intended, source MAC address, specifies the node sending the frame, and type field, also known as ether type, which indicates the upper layer protocol type, such as an IP version 4 packet. There is another type of frame that has a length field instead of the ether type, but it won't be discussed here. Ethernet also adds a field called frame check sequence, or FCS, to the end of the frame. The FCS is used to detect corrupted frames. Generally, when corrupted frames are dropped, Ethernet doesn't retransmit them. This is the responsibility of upper layer protocols such as TCP. The number listed under each field represents its size in bytes. We've just seen the structure of a standard Ethernet frame, which is composed of a payload encapsulated with a layer 2 header and trailer. In addition, the standard also defines that the payload size is in the range of 46 to 1500 bytes. The maximum payload size is also referred as the maximum transmit unit, or MTU. Frames with more than 1500 bytes payload are considered jumbo frames. Jumbo frames are not a standard, though supported by some vendors. Adding the 14-byte header plus the 4-byte trailer results in an overall Ethernet frame size in the range of 64 to 1518 bytes. Any frame less than 64 bytes in length is considered a collision fragment, or runt, and is automatically discarded by the receiving nodes. In order to understand how Ethernet frames are forwarded in the network, we first need to understand the role of Ethernet switches in networking. An Ethernet switch is a hardware device with multiple ports that connect Ethernet nodes. There are different types and sizes of switches, with different number and speed of ports, depending on the switch vendor and specific model. Ethernet nodes may have one or more Ethernet switches connecting between them. So, how are frames forwarded from a node with MAC A to the node with MAC B that have a single switch between them? When node A generates an Ethernet frame and sends it on the wire, that frame is received by the switch. The switch needs to learn where MAC B resides, or in other words, on which of its ports the frame should be sent. It seems like an easy task if both source and destination are directly connected to the switch. But what about nodes that have multiple switches between them, like nodes B and F? In this scenario, the switches need to know the whereabouts of nodes that are not necessarily directly connected to them in order to successfully forward the frames in the network. An Ethernet switch forwards frames based on the destination MAC address in the frame. But in order to be able to do so, it needs first to identify where those MAC addresses reside. The learned MAC addresses are stored in a database called the MAC address table that contains destination MAC address to exit port mappings. Let's see how MAC address table entries are populated, and then how they are used by the switch to forward frames. In this example, node A sends a frame to node B. The frame is received at the switch on port 1. The switch looks at the source MAC address and adds an entry that maps MAC A to port 1. Now if node C sends a frame to node A, the switch has a pre-learned entry for destination MAC A and the frame is sent on port 1. Dynamically, learned entries have an aging time, meaning if they are not used within a defined time, they are flushed from the table. Ethernet switch vendors do allow the adjustments of the aging time. Also, static entries can be configured. Static entries are not aged out and will remain in the table until manually removed. We've just seen how the MAC address table is populated with destination MAC to exit port mappings that are later used for frames forwarding, but it happens occasionally that there is no matching entry in the MAC address table. Those frames are called unknown unicast frames. Unicast addresses represent a single interface in a network. So what does a switch do with unknown unicast frames? For example, when node A sends a frame to node D. In this case, the switch will flood the frame, that is, send the frame on all its ports except for the incoming port. Frames for which their destination MAC address have a matching entry in the MAC address table are called known unicast frames. They will be sent on the specific port. A broadcast address represents all nodes in the network as the destination. Broadcast frames are identified by a special MAC address where all bits are set to 1. The hexadecimal representation is all 12 digits set to F. When the switch receives broadcast frames, it floods them. A multicast address represents a selected group of destinations in the network. Multicast frames are identified by special MAC addresses, where the least significant bit of the first octet is set to 1. Traditionally, Ethernet switches don't have the logic to forward multicast frames to the designated group members, hence they are flooded. Traditional switching operates at layer 2 of the OSI model, where packets are sent on a specific switch port based on destination MAC addresses. Routing operates at layer 3, where packets are forwarded based on destination IP addresses. Often referred to as a multi-layer switch, a layer 3 switch combines the functionality of a switch and a router, thus adds flexibility to the network. There are different considerations of whether to design the network as a layer 2, layer 3, or a combination of both. We'll cover some of those in the next unit. Welcome to the Data Center Design Considerations course. The purpose of this unit is to equip you with the basic knowledge to understand the main data center requirements and how they can be fulfilled. We'll start with defining what is a network topology and what are the considerations when choosing the right topology for one's needs. Then we'll present two design approaches: the hierarchical network design, that is considered the traditional design, and the leaf spine used in modern data centers. Later, we'll compare layer 2 versus layer 3 designs and understand how their behavior and protocols impact network performance. Let's start with an overview of general data center design considerations. A data center is a facility used to house computer systems and associated components, such as compute, network, and storage systems. A data center can be the size of a small server room to a few buildings geographically distributed. The data center is a critical business asset where companies run their workloads. The modern data center has evolved from a facility containing an on-premises infrastructure to one that connects on-premises systems with cloud infrastructures where networks, applications, and workloads are virtualized in multiple private and public clouds. Data centers require scalability, resiliency, and security. The modern data center is also becoming more technologically advanced to provide better efficiency. Data center design is the process of planning all of a data center's essential computational and non-computational parameters. Some are listed here: number and type of required servers, network layout, power, cooling, and ventilation systems, physical data center security, disaster recovery, and business continuity planning. Modern data center design will incorporate many different aspects that will make it easy to manage and more efficient. We won't cover in this unit all data center design aspects, but we will focus on networking considerations. One important design aspect is the network layout or topology. A network topology is the schematic arrangement of elements, such as links and nodes, which ultimately constitutes the structure of the network. It describes not just how devices on the network are connected, but also how data moves from one node to another. The following are key considerations when choosing a network topology. Availability. Enterprises that run critical applications need maximum availability of their network resources. High availability features must be considered throughout the network. Hardware and software, network protocols, as well as environmental and power features all contribute to the overall availability of the network. Reliability. In many of the industries, even brief downtime and delays are unacceptable. For this reason, network reliability is a fundamental consideration. Performance. The topology of a network is key to determining its performance. Choosing the right topology can increase performance while making it easier to locate faults, troubleshoot errors, and more effectively allocate resources across the network. Future growth. If the network is expected to grow in size in the mid to long term, choose a network topology that's easy to add new nodes without negatively affecting performance or the user experience. Budget. You can choose a topology that is perfectly suited to your needs, but it may not be affordable. There will probably be a lower priced alternative that's nearly as effective. The hierarchical design separates a network into distinct layers, where each layer has its role in the network. This hierarchical network design is most effective for north-south traffic patterns, where a majority of the data goes in and out of the data center, such as client-server applications. The model scales somewhat well because of its modularity, but may be subject to bottlenecks if uplinks between layers are oversubscribed. Cloud computing, virtualization, big data, and related trends have come together to transform data centers. Modern data center environments are becoming much more dependent on east-west traffic, as more data moves between servers and storage nodes in order to meet end-user demands. The network design needs to serve the modern data center's increasing demand for server-to-server communication, scalability, and resiliency. In the past few years, many data centers have transitioned to a leaf-spine design to overcome the limitations of the hierarchical design. A leaf-spine architecture is a two-layer full-mesh topology composed of a leaf layer and a spine layer. The spine switches connect the leaf switches with one another, whereas the leaf switches connect servers to the network. For that reason, the leaf switches are also referred to as the top of the rack switches, or TORs. Every leaf switch is connected to every spine switch, and obviously vice versa. The leaf-spine architecture has many advantages as listed here. If the network reaches a certain scale, a third level of switches should be considered. In this case, the upmost level, called the superspine or core, is used to interconnect the spine switches. But yet the same rules apply. Now that we know that the leaf-spine design is the best choice for modern data centers, let's see whether the network should be configured to operate at layer 2 or layer 3. We'll start with layer 2. In a layer 2 network, networking devices are configured for switching, meaning they make layer 2 forwarding decisions. They build and maintain a MAC address table that maps MAC addresses to exit ports. The switches process Ethernet frames and forward them based on the destination MAC address that is matched against the MAC address table. Overall, a layer 2 network does not scale well and provides lower bandwidth and performance than a layer 3 network. Also, it's harder to achieve redundancy and multipath support. We'll explore the reasons for that in the following slides. Let's focus on redundancy and multipath support. A redundant network design allows for network availability by duplicating elements such as switches or links, so that if an element fails, critical applications are not disrupted. Redundancy attempts to eliminate any single point of failure in the network. In this example, each leaf switch has a link to each of the spine switches, so that there are two available paths for the host to communicate. Let's assume that when host A communicates with host C, the path is via spine 1. But what happens if the link between leaf 1 and spine 1 fails? There is another available path via spine 2 that can now be used for traffic forwarding. This is the idea of a redundant network design. There is an active path and a backup path. If the active path fails, the backup path takes over. But if there are two available paths, why not use them both at the same time? This will allow for load balancing the traffic, hence providing twice the bandwidth and better resource utilization. This is the advantage of multipath support. Multipath is a strategy where traffic forwarding to a single destination can occur over multiple paths. It can substantially increase bandwidth by load balancing traffic over multiple paths. However, it may be difficult to deploy it, especially in a layer 2 network. Let's examine the reason for that. We already know that a redundant network design requires additional redundant layer 2 links to provide a backup path in case of a link or switch failure. Those redundant links allow multiple paths between a pair of nodes. Well, that sounds terrific because that's exactly what we're trying to achieve. But because of the behavior of layer 2 networks, this creates a layer 2 loop that eventually results in traffic denial. Let's see how it's caused. You probably recall from the previous unit how broadcast frames are handled by the switches. They are flooded in the network. If there are loops in the network, the broadcast frames circulate endlessly in the network, consuming all available bandwidth. This phenomena is called a broadcast storm, and it must be avoided. Otherwise, bandwidth is unavailable for normal network traffic. So, the simple conclusion is that a redundant layer 2 network design causes broadcast storms. Does that mean we can't have a redundant layer 2 network? Not exactly. We can and should have a redundant physical design, but logically there can only be one active path at a time between any pair of end nodes. We'll now present the protocol that provides this capability. Spanning Tree Protocol, or STP, ensures a loop-free logical topology for Ethernet networks. It allows a network design that includes redundant links and provides automatic backup paths if an active link fails. STP achieves that by identifying redundant links and putting the redundant ports in blocking state. Then, when a topology change occurs, STP reacts and moves blocked ports to forwarding state. It is important to mention that the convergence time of STP is between 30 to 50 seconds, during which data traffic is not served. Maybe this convergence time was acceptable in the 1980s when STP was initially developed, but no modern data center can tolerate such a long convergence time. Rapid Spanning Tree Protocol, or RSTP, was introduced in the 1990s to provide rapid recovery after a topology change. There are different enhancements to support faster convergence, and we won't discuss the details here. In general, RSTP allows the switches to almost immediately react to a topology change and start negotiating port states. In addition, RSTP provides alternate ports that immediately move to forwarding state, if a port becomes unavailable. This and more allow RSTP to respond to changes within a few seconds or as fast as a few milliseconds on a physical link failure. To summarize, both STP and RSTP allow a redundant network design by providing a single active path at a time. The backup paths are not used at all as long as the network is stable, and the additional bandwidth is wasted due to blocked ports. In order to allow a Layer 2 network design to provide multipath support, a third version of STP was introduced. Multiple Spanning Tree, or MST, enables configuring multiple STP instances with a group of VLANs mapped to each instance. MSTP settings can be configured so that each instance has a different active path. In our example, the green path is the active one for VLANs 1 through 50, and the purple path is the active path for VLANs 51 through 100. When hosts A and C in VLAN 2 communicate, the traffic will take the green path via spine 1, but when hosts B and D in VLAN 68 communicate, the traffic will take the purple path via spine 2. In this way, we achieve load balancing and multipath support, hence better overall network utilization. Sounds awesome, but in practice, as the network scales, it becomes very difficult to manage multiple MST instances. Another Layer 2 feature to achieve higher bandwidth, load balancing, and redundancy is a link aggregation group, or LAG. LAG, also known as port channel or bonding, enables the aggregation of multiple physical ports into one logical port. The benefits of link aggregation include the following. Higher bandwidth. LAG provides the bandwidth that is the sum of the physical link's bandwidth. Load balancing. Traffic is distributed on all physical links, which are part of the LAG. High availability. When a physical link fails, other links of the LAG continue to serve the traffic. While LAG provides aggregation of physical links that reside on the same switch, multi-chassis LAG or MLAG allows for the aggregation of the physical ports of two separate switches into one logical port. MLAG switches appear as a single Layer 2 switch. The dual connected device, host, or switch runs a standard LAG and is unaware of the fact that its LAG is connected to two separate switches. MLAG provides high bandwidth and load balancing, high availability in case of link failure, and high availability in case of switch failure or switch software upgrade. Let's now summarize what we've learned about a full Layer 2 network design. We need to configure MSTP for multipath support and MLAG for redundancy. While it may be a simple design, well understood and easy to configure on a small scale, Layer 2 protocols are difficult to manage at scale. The design may be suitable for traditional enterprises with few network needs. The conclusion is that for scale-out modern data centers, a Layer 3 design would be more suitable. Let's now explore the reasons for that. In a Layer 3 network design, routers or Layer 3 switches are configured for routing. If you recall from previous units, routers build and maintain a forwarding database called a routing table that maps remote IP networks to next-hop routers. The routing table is populated by configuring static routes or by enabling a dynamic routing protocol such as OSPF or BGP that will be introduced later. Routers then forward IP packets to their destination based on the routing table entries. Achieving load balancing and multipath support in a Layer 2 design is very difficult. It involves a combination of STP and MLAG settings that are hard to maintain in large networks. In a Layer 3 design, it's much easier since routing protocols have built-in mechanisms for identifying and eliminating routing loops. Thus, a Layer 3 design provides redundant active-active links with no blocked ports. Routing protocols also support equal cost multipath, or ECMP. ECMP is a routing strategy that allows packet forwarding to a single destination over multiple best paths. In addition to that, IP packets carry a time to live, or TTL field, that is used to avoid packets endlessly circulating in a loop. If an IP packet ends up in a routing loop, it can traverse 255 hops, or routers, at most, before it is discarded. When choosing a routing protocol to be used in the data center, there aren't too many options to begin with. Preferably, an open standard, scalable, and robust protocol should be chosen. When comparing the two most commonly deployed routing protocols, OSPF and BGP, BGP is the routing protocol of choice in modern data centers. We won't go into the details of these protocols, yet we will highlight some properties in favor of BGP. BGP is the routing protocol that makes the internet work. BGP allows service providers to exchange routing and reachability information so that packets are routed on the internet. It is designed for scalability and stability in very large networks. BGP is an increasingly popular protocol for use in the data center, as it lends itself well to the rich interconnections in a leaf-spine topology. The following are some notable BGP properties. BGP does not require a routing state to be periodically refreshed, unlike OSPF. It has many robust vendor implementations. BGP is a thoroughly tried and tested protocol that comes with years of operational experience. Now that we're convinced that a Layer 3 network design is more suitable for our high-demanding scaled-up modern data center, let's see two design options. The first one would be a combined Layer 2, Layer 3 design. Here, the leaf, Tor switches, operate at Layer 2 towards the nodes with MLAG for redundancy. The uplinks from leaf towards the spine switches operate at Layer 3 with ECMP to provide scalability, redundancy, and load balancing. These designs are simple, well understood, and easy to configure, but still use Layer 2. Typical deployments would be data centers and big enterprises, high-scale bare metal hosts, high-scale virtualized hosts. The second option would be a full Layer 3 from host to leaf spine with routing and ECMP for redundancy even at the host level. A very high level of scalability and redundancy is provided, and we've eliminated the need for Layer 2 protocols. One drawback is that it may somewhat complicate host administration since it requires a routing protocol to run on the hosts, also referred to as routing on the host. Typical deployments for this design would be a highly virtualized environment with a high degree of host mobility. We've completed the unit. Thank you for watching.